Okay, now.
Yeah, sure. No.
Welcome to the AGU GeoHealth Early Career webinar. The title of today's webinar is the application of satellite data in GeoHealth studies. And it is an honor and pleasure for me to introduce our guest speakers, Dr. Xiaomeng Jin and Dr. Navid Jadidoleslam. Dr. Jin earned her PhD in 2020 from Columbia University in Earth and Environmental Sciences, and she is currently a postdoctoral fellow of NOAA Climate and Global Change at University of California, Berkeley. Her research primarily focuses on air pollution and its health impacts, and today she will present her work on using satellite data to understand the ozone chemistry. On the other hand, we have Dr. Jadidoleslam, who earned his PhD recently in 2021 from University of Iowa in water resources engineering. He is currently a postdoctoral fellow at Georgia Institute of Technology. And his research is primarily focused on using soil moisture data in improving flood predictions. And today he will elaborate this using satellite data. I am excited to listen to these two great talks. But first, let's go through some housekeeping items. So the format of the webinar is that first Dr. Jin and then Dr. Jadidoleslam will present their research. And afterwards, we will have a moderated Q&A session. So if you have any question, please find the participant named Ask Questions here in the participant list and forward your questions to her in chat. We will compile and organize the questions and I will ask them as far as time permits. And please keep your audio and video off so that we keep the bandwidth. And finally, this webinar is being recorded and will be posted on AGU YouTube channel shortly, probably next week. With that, I stop sharing my screen and hand it over to Dr. G. Take it away. Thanks.
Thank you, Bruce. Yeah, can you see my screen?
Yes, we can. Go ahead.
Okay. Hello, everyone. Thanks very much for the invitation to present my research here. So today I'm going to talk about my research on using satellite data to guard the emission control strategies for surface ozone pollution. So to begin with, over the US, there have been a lot of efforts made to improve the air quality in the past decades, which has led to more than 74% reductions of the emissions of common air pollutants. So this progress occurred at the same time while the US economy continues to grow, people drive more, population and energy use both increase, which is good news, but there's still more work to be done. So even with the improved air quality, there are still 82 million US people living in areas where the air quality does not meet the standard. So among different air pollutants, there are about 74 million US people living in areas where the ozone does not meet the standard. So this figure shows the map of the ozone non-attainment areas in the US. And you can see that many metropolitan areas, such as New York, Chicago, Denver, and also many counties in California are all in the ozone non-attainment areas. So this then brings the question about why is it challenging to control ozone pollution in these counties? And this is actually a long-standing question in our field, which has been studied for more than decades. But today I'm going to talk about this issue from the perspective of using remote sensing observations. So now currently we have entered the satellite era, and the suite of the emerging satellites has provided us with an unprecedented opportunity to study the Earth. So here I'm showing you the NASA Earth Science satellite missions through 2023. And so I'm not going to expand on all of them, but I just want to say that each satellite has its unique design and also the purpose. Some satellites like Alpha, Terra, Aura, so these satellites have already been launched for more than a decade. And some satellites like these satellites here, Temple, Maya, they are planned to be launched in the near future. So the remote sensing of the atmospheric composition relies on observing the backscattered solar radiation or the thermal infrared emissions from the Earth. So basically, the remote sensing of the trace gases relies on observing the spectral signatures of gas absorption. Some gases, such as formaldehyde, SO2, they have unique spectral signatures at the UV wavelengths. Some, like NO2, absorbs visible light. Others, like CO2, methane, CO, they have stronger spectral signatures at near infrared to thermal bands. So the retrievals of these trace gases is essentially an inverse radio transfer problems, which solves the composition of these trace gases that can best match the measured spectral signatures from satellite instruments. So this animation, for example, shows you the NO2 level observed from the ozone monitoring instrument, OMI, which is aboard the Aura satellite. And you can see that there is a sharp decline of NO2 across the US. So this is actually a very good demonstration of the success of emission control, which has been implemented in the past decade. So since I'll be talking about ozone today, so I want to first clarify a little bit which ozone I'm talking about, because ozone plays very different roles in atmosphere depending on where they are located. So in the atmosphere, more than 90% of the ozone resides in the stratosphere, which forms the ozone layer. And when we talk about the ozone hole and we know how it's bad, we are talking about the ozone in the stratosphere. So in the upper troposphere, ozone is an important greenhouse gas. And in the lower to middle troposphere, ozone is a source of hydroxy radicals, which is a cleanser of atmosphere, which can remove the air pollutants and also some reactive greenhouse gases like methane. So the ozone I'm talking about today is actually the near surface ozone, which is a main component of the photochemical smog, and it's damaging the human health and the vegetation. So back to the remote sensing, we know that while satellite instruments can retrieve the total column of ozone, more than 90% of ozone resides in the ozone layer. So the contribution of the near surface ozone is just too small to be detectable with current satellite instruments. So this then brings the question about how we can connect satellite observations with near surface ozone. So to answer these questions, I want to first introduce the ozone chemistry. So the ozone near the surface is formed from the photochemical reactions between two classes of ozone precursors, NOx and VOCs, in the presence of sunlight. So the NOx are generally emitted from fossil fuel combustions, and some can also be emitted from natural sources like fires, lightning, and soil. And the VOCs refer to the volatile organic compounds, or the organic compounds in the vapor phase. So while the anthropogenic activities can emit some VOCs, but globally more than 90% of the VOC emissions are from the biogenic activities from trees. So the ozone production is dependent on relative abundance of NOx versus VOCs. So to control ozone pollution, an important question we want to ask is whether the ozone formation is limited by NOx or is limited by VOCs. So we know that the VOCs consist of hundreds or perhaps thousands of different organic compounds. So it's very difficult to measure all of them. But back in 1995, Sanford Xiaomeng proposed some secondary species as indicators of NOx and the VOCs. So two of them are nitrogen dioxide and formaldehyde. So this is because NOx mainly exists in the form of nitrogen dioxide in the boundary layer. And for VOCs, the formaldehyde is a common intermediate oxidation product of many VOCs. So it's generally considered to be proportional to the reactivity with VOCs. So these two species have been proposed decades ago, but these are especially useful today because they can be retrieved from space as the NO2 tropospheric columns and also as the formaldehyde column. So studies have used the ratio of the formaldehyde to nitrogen dioxide to diagnose the ozone NOx VOC sensitivity. So in general, when the ratio of the formaldehyde to nitrogen dioxide is high, it often means the ozone production is NOx limited. where the NOx emission reduction is more effective than the VOC emission reduction. And on the other hand, when the ratio is low, it often means the ozone production is VOC limited or NOx saturated, where the VOC emission reduction is more effective, while the NOx emission reduction is actually counter-effective because of the NOx titration effect. So this is the basic idea of using the ratios to diagnose the ozone chemistry. So it's simple to use, and basically you can apply this everywhere in the world. But the question is how high is high and how low is low? That is to find the threshold values to separate these two regimes. So to show you how we can quantitatively link the satellite-based ratio with ozone chemistry, I want to first introduce you with this ozone isoclass. So this is a classic way to describe the nonlinear dependence of the ozone production on NOx versus VOCs. So in general, when the NOx is low, when the ozone production is limited by NOx, when we increase NOx, we can see that the ozone production also increase. But increase of VOCs almost have no effects on ozone production. As we further increase NOx, when we reach these areas, the VOC limited regimes, we can see that the increase of the VOC activities leads to increase of ozone, but increase of NOx is actually leads to a decrease of ozone. So this is because that at the VOC limited regimes, when there is a lot of NOx in the systems, the NOx can actually consume the hydroxyl radicals, which is needed for oxidation of many VOCs, so that it can slow down the ozone production. So this is how the ozone production is non-linearly dependent on its precursors, NOx and the VOCs. So this kind of isoclass is generally derived from analytical models based on theory. So we want to know if we can also mimic the similar patterns using the real-world cell observations. So to do so, we have collected millions of ground-based observations of ozone from the EPA AQS network, and then we aggregate these observations according to their corresponding NO2 and formaldehyde, which are sampled from daily OMI satellite observations. And then for given formaldehyde and NO2, we then calculate the probability that the ozone is higher than 70 ppb, which is the EPA standard for ozone. And we can also call this as ozone exceedance probability. And so we can see that this figure generally captures the patterns of this ozone isoclass. At the high formaldehyde to NO2 ratio, which is this area, we can see that the ozone exceedance probability decreases with lower NO2, which means that the ozone exceedance is less likely to occur with NOx reduction, which indicates NOx limited regimes. Over this area, when the ratio is lower than 2, we can see that the ozone exceedance probability increases with lower NO2, which indicates NOx saturated chemistry. And we can also see that there is no single threshold to separate these two regimes, which is likely to occur between 2 and 4. And we also find that there are some variations among different cities and different seasons. So in any case, we call these regions as the transitional regimes, which is actually where we find the highest ozone exceedance probability, which means that the ozone production is most efficient as the transitional regime. So now since we have built a methodology, so the next step is to look at the long-term evolution of ozone sensitivity over the US urban areas. So the ozone monitoring instrument, which I just talked about, was launched in 2004. But to go back further in time, we also included 2 other satellites, including GOM and Xiaomeng. So these 3 satellites together give us more than 20 years of continuous observations. So in order to ensure the consistency across different satellites, we have developed a new method to harmonize these satellite observations for formaldehyde and NO2. So this harmonization algorithms accounts for 3 potential issues that can lead to discrepancies across different satellites. This includes the consistency of the retrieval algorithms, the difference in overpass time, and also the difference in the resolution. So for the interest of time, I'm not going to talk about the details of the harmonization, but just want to show you the results that are based on the satellite-based formaldehyde to NO2 ratio. So this figure shows you the summertime multi-satellite formaldehyde to NO2 ratio over the US in 2 different periods, 1996 to 2000 on the left, and 2013 to 2016 on the right. So if you find any blue to green areas, it means the ozone production is VOC limited or NOx saturated. In yellow to brown means it's transitional, and the brown to white areas are NOx limited, which you can find over most rural areas in the US. We can see that in the early period, The many US cities are in the VOC limited regimes, where there is a lot of anthropogenic NOx emissions from phosphor combustion. However, as a result of the emission control, we found that many US cities have already made the transition to the NOx limited regimes in the recent period. For some cities like New York, Chicago, and Los Angeles, while we can still find the VOC limited chemistries in the urban cores, the transition of the VOC limited from VOC limited to NOx limited regimes has moved towards the city center. So what does this mean? It means that in the early period, for the cities where the ozone formation is VOC limited, it's more effective to control VOC emissions to mitigate ozone pollution. The reduction of NOx emissions could actually make the ozone even worse. But this doesn't mean that we should not control NOx emissions, because in the long term, as these cities are making transition to the NOx limited regimes, the NOx emission control would then become effective at reducing ozone pollution, which is actually the current situations in many US cities. So this is also to say that the benefits of the NOx emission control would become larger and larger as we further decrease the NOx emissions. So to look at this in another way, here I'm showing you the satellite-based NO2 as a function of distance from the city center in two different periods, 1996 to 2000 as a dashed line and 2013 to 2016 as solid line. And you can see that there is sharp gradient, urban-rural gradient of NO2 in both periods, and the gradient is smaller in the recent period. Formaldehyde, on the other hand, doesn't show much urban-rural gradient, and we even see the small increase of formaldehyde in the recent periods. So this is largely because the formaldehyde is largely from the biogenic sources, which doesn't show much trends in the past decade. And as a result, the ratio of the formaldehyde to nitrogen dioxide has increased in the recent period, which leads to the regime transition, which is the intersections between the gray band and the red lines to move towards city center from around 120 kilometers away from city center to around 30 kilometers away from city center. So to connect this with the near surface ozone, so this figure shows the summertime mean ozone from the in situ environments, again, in two different periods as a function of distance from the city center. And you can see that in the urban areas, in the urban populated urban cores, where the ozone formation is not saturated, we can see that there is actually an increase of ozone in recent period compared with the early period. Further away from the city center, where the ozone formation is NOx limited, we can see that there is a large reduction of ozone in recent period. And in the early period, the ozone peaks around 120 kilometers away from city center, which is consistent with the regime transition diagnosed from satellites. And in the recent period, the peak ozone has moved towards city center to around 20 to 40 kilometers away from city center, which is again consistent with the regime transition diagnosed from satellites. So the consistency between these two just gave us more confidence that our approach is able to diagnose both the spatial and the temporal variability of ozone chemistry over urban areas, which means that this method can also be applied to other regions with no monitors. Okay, so back in 1980s, so people have noticed an interesting phenomenon that in many US cities, the ozone is always higher it's generally higher on weekends than weekdays. So this is because on weekends, as there is less traffic, the NOx emissions also decrease. But for those US cities where the ozone formation is NOx saturated, the NOx emission reduction on weekends could actually make the ozone higher. And we call this as the ozone weekend effect. So this figure here shows the difference in the summertime mean ozone on weekends minus weekdays. And this figure shows the corresponding formaldehyde to NO2 ratios in seven different cities and in 5 different periods. And you can see that as these cities are making transition to the NOx limited regimes, we found that there is a reversal of the ozone weekend effect in many cities like Chicago, New York, Pittsburgh. And for Los Angeles, while we can still find the positive difference on weekend minus weekdays, the magnitude of the ozone weekend effect has become much smaller in recent periods. So this again tells us that these US cities are making the transition to the NOx limited regimes. So up until now, all our analyses are either based on aggregations of long-term cell observations to reduce the noise of cell retrievals. Actually, the daily single observations from these satellites are often noisy and it's affected by clouds. So in October 2017, the Omi, which is on board the Sentinel-5P, just launched to space. So this new generation satellite instrument has finite spatial resolution and with improved signal-to-noise ratio. So this really has the potential to allow us to see the short-term variability of ozone chemistry. So to show you how we can use this Omi data to look at the short-term variability of ozone chemistry, here I'm just going to give you an example. So these figures show you the Omi retrieved NO2 and formaldehyde over the Northern California on November 8, 2018. So the day when the California campfire started. So you can see that there is plumes coming from the fires going all the way to San Francisco. So the arrows here, I'm showing you the high-speed derived trajectories of these plumes at different altitudes. And you can see that the transport of the emissions mainly follows the trajectories at high altitudes between 2,000 and 3,000 meters, which means that the campfire injects a lot of emissions into the free troposphere. So how can we link this with this ozone chemistry? So this figure shows you the day-to-day variability of NO2, formaldehyde, and the formaldehyde-NO2 ratio in two counties, the Butte County, which is the county where the fire occurred, and San Francisco, which is downwind urban areas. So before the fires, the ozone production in San Francisco is VOC limited, which is typical for urban areas in November. And in Butte, the ozone formation is NOx limited before the fire, where there is little anthropogenic NOx emissions. And on the day with fire, we found that there is a large increase of both NO2 and formaldehyde in Butte County. And the increase of NO2 is larger than the increase of formaldehyde, which as a result leads to the regime transition from the NOx limited regimes to the VOC limited regime. And on the following days, we see that there is a further increase of the ratio, which leads to the regime transition going back to the NOx limited regimes. And for San Francisco, it's a different story. And before the fire, the ozone formation is VOC limited. But on November 8, we found that the fire has led to a large enhancement of formaldehyde, but not so much for nitrogen dioxide, which as a result leads to the regime transition from the VOC limited regimes to transition regime. And we see a further increase of the ratio on the following days, which leads to the regime transition from the transition regimes to NOx limited regime. So of course, there are still a lot of unknowns as how the fires influence on the ozone chemistries and how the aerosols from fires influence the chemistries. So this is what I'm currently working on. So, but in any case, I just want to show you how we can use satellite observations to diagnose the day-to-day variability of the ozone production regimes. So that's all I have for today. And to briefly summarize, we have shown the value of using remote sensing observations to diagnose the nonlinear chemistry of surface ozone in urban areas. And we show that as NOx emissions decline, the most US cities have made a transition to the NOx limited regimes. And we also shown how we can use the Omi observations to look at the short-term variability of ozone chemistry due to wildfires. And wildfires emit large amount of ozone precursors, which can lead to a large change of ozone production regimes over both source and the downwind urban areas. So that's all I have. Thank you very much for listening, and I'm happy to take any questions.
Thank you very much, Dr. Jin. But I think in the interest of time, it's better that we first listen to all the presentations and then go to the questions. So if Dr. Jadidoleslam could share his screen.
So do you hear me well?
Yes, we can hear you. And it looks good.
Yeah.
Go ahead.
So today I'm going to talk about the utility of the satellite-based soil moisture in real-time flood forecasting. And this work has been one of some part of my PhD thesis at the University of Iowa, where I was working at the Iowa Flood Center. This first title slide actually shows the two satellites that I have worked during my PhD. And the right-hand side is SMAP, soil moisture active passive. And on the left-hand side, you can see SMOS, or soil moisture ocean salinity. This figure or illustration is actually showing what I'm trying to do, is that before the flood occurs, we want to have an observation from one of these satellites, potentially, to improve the flood forecasts. But before going into flooding and other details, I should talk about the soil moisture and the flooding as well. So the floods are one of the most damaging natural hazards that are occurring around the globe, and it's important to predict it well, and that's satellites can help us in improving those predictions. And specifically, I'm looking at soil moisture, which is a key variable in determining or giving the amount of water that will go into soil, or it will run off over the surface, or simply called partitioning of rainfall runoff. Soil moisture is a water that inside the soil, and you can think of it, you can think of soils as buckets. If the bucket is full and there is rainfall on top of it, it will run off and it will, fill up, and then it will flood basically in the real world. The other part of the spectrum is that the soils are very dry, or that bucket is empty. So that understanding how much water that bucket has is important, and actually it's just an analogy, but the soil moisture observations are very important for flood and drought forecasting. However, soil moisture observing soil moisture, because of its variability, high spatial variability, is very challenging. And that's why in 2010, soil moisture ocean salinity was launched by European Space Agency. And SMAP, soil moisture active passive, which has a different kind of instrument and observing technique, has been launched in 2015. These two satellites operate at 1.4 gigahertz frequency. They observe brightness temperature, essentially. Brightness temperature is the electromagnetic property of a material. And these sensors observe brightness temperature, and using other ancillary observations or data, they try to estimate the soil moisture over the globe. However, their resolution in space is coarse. Like the SMAP has 36 kilometers in space, resolution in space, and soil moisture ocean salinity, or SMOS, has 43 kilometers on average, the spatial resolution. The good thing is that they are observing the soil moisture, or this hydrologic variable, in global scale. This image specifically shows soil moisture observation or estimations from SMAP over the 2 to 3 days. This is a composite image of the soil moisture. And what we can see here is that these features in global scale, where the precipitation patterns are more dominant, and we can see those locations have higher, wetter soils. So, research is being driven by some of the motivations. That motivation in here is the spatial resolution, the first part of the talk, which I will talk about a little more later. In here, I'm showing the spatial scale mismatch. What does it mean? It means that our modeling purposes uses a heliotrope, or a discretization of space or landscape, in the order of 0.3 kilometers squares. Well, on the left-hand side, you can see enhanced resolution SMAP scale, which is in the order of 9 kilometer by 9 kilometer resolution. What we can see here is that the information is being lost, and actually that information that we need is what we need is more finer scale, and this is coarse. That's the first issue in satellite remote sensing. That is, it exists in other satellites as well, but soil moisture has higher variability. That's why it's more important, at least for for hydrologic purposes. The other issue is that soil moisture or the brightness temperature observations is impacted or affected by vegetation water content. Vegetation water content is the water that exists in the stem, leaves, and the structure of the vegetations and plants. So that actually affects the radiation that goes out from the surface of the soil to outer atmosphere and hits to the sensor. So that's the first issue. These issues, this issue is more pronounced in an agricultural region such as Iowa. And another thing is that these satellite soil moisture observations are more applicable in like the agricultural places, because we need to understand how much water we should put into the water or irrigate essentially. And that's why if there is noise in the satellite or these are spatially averaged, then we need to have some plan for that or understand what's going on. The other issue is the surface roughness, which I'm showing a device that observes, or we can measure the surface roughness of the soil. So because of the tillage in the agricultural regions, it affects the accuracy of the satellite observations for the soil moisture. Well, the two elements in my research tries to address that. The first element was the mismatch or scale mismatch. And I try to understand how much variability we have in a grid or satellite grid scale. Essentially, the question that I'm interested in, or we are interested in, is that what is the information content of that 9 by 9 kilometer or 36 kilometer by 36 kilometer averaged, spatially averaged satellite-based soil moisture? To understand or answer this question, we can use some of the soil moisture observations in the field. So I use soil moisture sensors at 5 centimeter at the top layer, which is more relevant to satellite observations, and precipitation observations from the dual tipping bucket rain gauges over the Iowa, which is an agricultural region. I have two watersheds. So for example, if we go to one of these sites and plot the data for the precipitation and the soil moisture, we can see how much precipitation affects the soil moisture dynamics. At the bottom plot, I'm showing the time series of the soil moisture anomalies or changes. And basically, when there is a precipitation, soil moisture increases, which we call it wetting period. And then there is no rainfall, and because of evaporation and evapotranspiration and drainage, soils dry down. So those are the two phases of the soil moisture dynamics. We can fit a power law equation or curve and to try to model this behavior from the soil moisture observations that we have. So we did that, and we created a model that uses MRMS or multi-radar, multi-sensor national product from US to force the rainfall to feed the model and to generate the time series or provide the soil moisture estimates at hill slope scale and using the Polaris soil properties as well. What you can see here is this, again, how much we only have SMAP observation, one value, and there are multiple hill slopes in that grid. So if we do that and model the soil moisture at each hill slope for each of those basins or watersheds and plot it in terms of mean or average soil moisture versus standard deviation of the soil moisture. We can see a curve like this cloud of points that are changing, starting from 0 to 1. These are normalized soil moisture. And what we can see is that the maximum variability is occurring in the intermediate ranges of the soil moisture. On the other hand, we see that the standard deviation is very low for very wet conditions and very low, very dry conditions. And that applies to both of the basins or watersheds. On the right-hand side, this plot corresponds to a smaller watershed. Therefore, the watershed, the soil moisture variability is lower. So how this is relevant to application of satellite remote sensing? We want to understand or incorporate the uncertainty of that spatially average soil moisture coming from the satellite, which is essentially an average value over that 81 kilometers squares or 9 by 9 kilometers squared. Using this model, we can provide an uncertainty of standard deviation of how variable soils are at that, how much variability we can expect from the soil moisture estimations from the satellite. More details are provided in the paper. You can, I would be more than glad to share it with you. If you had any questions, we can talk. The next element was to understand basically how much information, again, how useful are these satellite estimations for predicting the runoff for the next few events. Well, this study was motivated by a paper from Dr. Kra et al. That they published in the GRL. Essentially, what we did, we used their approach and added a little bit more of analysis to understand better what happens in the agricultural regions in terms of predictive power of satellite-based soil moisture. So for doing that, we selected watersheds across Iowa, which we had USGS, the United States Geological Survey's observations for stream flow and stage. Basically, we used stream flow, and we took the average of the soil moisture from SMAP satellite, and also we had rainfall from stage 4, which is a national product. And if we plot these data together in two plots, at the top I'm showing the stream flow observations. These are daily values in one month, one of the months. So it shows how the rainfall occurs, and then when there is rainfall, the stream flow goes up and then goes down, recession, and then again, events basically happen when there is rainfall. So we can find out the total amount of water that goes into channels basically by separating out the stream flow to storm flow, which is a quick runoff, and to find out the runoff ratio. Basically, we have the observation of rainfall as well. So if we sum those two and then divide them together, we can find the runoff coefficient or runoff ratio. So for each event, we also have the antecedent soil moisture from satellite. These triangles show the soil moisture observation for the watershed average of The upward triangles show the ascending when the satellite is going northward, and the downward triangles means that the satellite is orbiting towards south. So if we do that for all of the basins or watersheds, and then plot the data of antecedent soil moisture versus the runoff ratio, we can see how they vary together, or what's the relationship between them. When there is higher soil moisture from these two plots, well, one of them is using stream flow, the other one is a storm flow. We just plot that to see how, if that affects the analysis, but it didn't affect the analysis. So these plots show that as the soil moisture goes to higher values, or if it's higher, then the runoff coefficient of upcoming event, rainfall runoff event, is higher, meaning that there could be a flooding for the next event if there is already water in the channel, and we need to take some precautions. And that showed that SMAP satellite provides significant information for predicting runoff production. And more details, I have also looked at the vegetation effect on the runoff production from Maurice. You can take a look at the paper as well. That's all I have. I wanted to make it short a little bit in the interest of time. And this project was funded by NASA, Science Utility of SMAP, and Iowa Flood Center, IAHR at the University of Iowa. Thank you so much for your patience, and I would be glad to answer any questions if you have.
That was great, Dr. Jadidoleslam, and I think right now we are ready to ask our questions. So if Dr. Jin could also turn on her video. Okay, so I will try ask questions one from each other. So the first question is for Dr. Jin, and actually this is my question, and I was wondering, so the ozone chemical regime is changing by location. I mean, it is different spatially. So the transition between VOC limited to NOx limited changes by location. So, and I saw that you had like a transition point for VOC limited or NOx limited. So how do you define that? And I was wondering if you consider the changes spatially in your analysis.
Okay, this is a very good question. So how to define the transitional regimes or the VOC limit regimes or different regimes is actually the big topic of this question. So and actually, so when we describe the different regimes, when we say NOx limit regimes and VOC limit regimes, it's kind of qualitatively to describe these regimes. But in my studies, so they are in the literature, there are different ways to define regimes. So some studies that they rely on models, and then they use the models to run perturbation simulations, and then they see how the ozone responds to the emission change in the models. And then they use this to define different regimes. And in our study, what we are trying to do is to use observations only to define the regimes. So what we are trying to do is say to first aggregate all the observations together and say that if we can see some general patterns at which the ratio is higher than given values, the ozone production is generally NOx limited. But it's not saying that, say we define the ratio regimes between 2 and 4, but it doesn't mean that if the ratio is 4, it also is always NOx limited. But it only means that it's more likely to be NOx limited than VOC limited. So it's not a hard threshold, and there is some transitions of the thresholds. And there are also some uncertainties with these thresholds to separate different regimes. And also you mentioned that the regime is very different for different locations. And this is really true. And we also find that depending on the VOC mixtures of different cities, so some cities may have more biogenic VOCs, other cities may have more anthropogenic VOCs. So depending on different mixtures of VOCs, the regime threshold values may be a little different. And also another thing is that we also find that there is also some seasonal variations of the regime transition. And how we define threshold values for different seasons is also another topic that I have early paper in 2017, which talk a little bit about how the seasonal variations of the regime transition. But in any case, even though we know that there are uncertainties with these threshold values and with how we define the regime transition, but what we are more confident is the overall trend of this ratio. It's over the US cities, we see that there is a clearly trend of the increase of the ratio, which means that the cities are making transition from the VOC limited to NOx limited regimes.
Thank you. That was a very good explanation. Okay, we have a question for Dr. Jadidoleslam, and I will try to read that so I don't miss any point. It says, I am interested to learn more about using soil moisture to improve flood forecasts. When I think about catastrophic flooding in the US, I think of urban areas, for example, New Orleans, and wondering how important soil moisture is there, since so much is, since so much is impermeable surface. Or is this more important in areas with more vegetation cover, like the Midwest?
Well, that's a good question. Well, satellite-based soil moisture cannot be much applicable in the urban areas because of the land cover or the type of the land on the surface, because it's mostly developed. It's not grass or no soil, generally talking. However, urban area or urban flooding does not occur from the cities only. That's the upstream problem that comes and washes away the cities. And mainly upstreams are not much urban or more developed. So if we take if we look at this problem or this question from this perspective, that it is the upstream that floods the downstream, which is the city, then still satellite-based soil moisture is useful. However, in urban areas, it's I don't think that much be useful directly. So it's still useful because we have a model that incorporates the satellite soil moisture observations and tries to improve this soil stream flow predictions at cities or the river stages that are close to cities. But that's a good question. Thank you for asking. Yeah.
Thanks for the nice explanation. And I didn't know that we cannot use soil moisture data for urban areas. Okay, so it brings me to the next question, which is kind of combined on both works, that we also have NOx emitted from soil. So I was wondering if SMAP or SMOS provides any information on the emitted NOx, or if Dr. Jin uses the soil NOx in her analysis in any capacity. I mean, either of you can answer that.
Well, Dr. Jin, do you want to start?
Okay, yes, I can talk a little bit.
Yeah.
So yeah, because I just introduced the Trop-Ohm instrument. So an advantage of the Trop-Ohm instrument is its improved spatial resolution and the improved signal to noise ratio. And there is actually a recent study that used Trop-Ohm NO2 data to derive NOx emissions from soil, and which is done by I forgot the name, actually from the U Michigan. So maybe I can send you the paper later. So what they have done is trying to use the Trop-Ohm NO2 data and to derive NOx emissions. And I know also in their paper, they are trying to somehow connect this with the soil moisture, because the NOx emissions is largely dependent on like environmental variables, which is not my expertise. But I just want to say that, yes, there are a lot of interest in using remote sensing observations to constrain the NOx emissions from soils. But in terms of my research, because I was mostly focusing on urban areas, so the contribution of soil NOx to the urban NOx is very negligible. It's almost negligible compared with anthropogenic NOx emissions. So that's not what I was interested in. But if you're thinking about the regional ozone pollution or the old areas where there are a lot of vegetations, agricultures, the NOx emissions would be more important to would be a contributor to the ozone pollution over those rural areas.
Yeah, that's a great answer, I would say. Although I would on top of that, I would add that as Dr. Jin as well pointed out, the transition or the soil-water movement depends on the antecedent soil moisture or current state of the soil in terms of the available water in the soils. If the water is higher, then that NOx transition to deeper layer, or if it's will be more facilitated based on if there is more water. On the other hand, if the water is lower, or the emissions from the soils, which was one of the problems in the agricultural region, such as Iowa, because they use a lot of fertilizers. It could be a research topic that for funding or something like that. But if there is lower soil moisture, then the evapotranspiration or evaporation from the soil still will be there up to some point, but evaporation from the soil will be, we can observe that quantity, at least indirectly, from the satellite-based soil moisture. So yeah, there is some room for work and collaborations.
Okay, thank you. We have one general question, I guess, for Dr. Jin, which says, do you know of any kind of technological advancements that can be built or have been built to help and control the VOC and NOx emissions?
Okay, that's a big question, and it's a very good questions, because this is not my expertise. This is more like the engineering side. But I just want to say that for NOx emissions, it's easier to control. So for many power plants in the US, they have already have this denitrification technologies where they can denitrify this NOx by applying, say, ammonia to react with NOx to reduce NOx emissions when they're coming out of this from the power plants. And for VOCs, VOC emission control is more tricky. So for one thing is that we know that VOCs consist of like hundreds or perhaps thousands of different VOC species. So it's very difficult to control all of them. And also there is like some industries, like solvent industries, they've already have like these technologies to reduce the VOC emissions. Like they apply some oxidizers to oxidize these VOCs to reduce these VOCs in the atmosphere. But a lot of VOCs are coming from the consumer products. So there is a recent study that's showing that the VOCs from the consumer products, like the hairsprays, cleaning products, they are making larger and larger contributions to the VOC and supersonic VOCs in the US, which are extremely difficult to control. And on the other hand, as I just mentioned in my talk, that more than 90% of the VOC emissions globally are coming from the biogenic activities from trees. So it's unlikely that we want to cut trees to reduce the VOC emissions from this source. So from that perspective, there is no control technologies for the VOCs from biogenic sources.
Okay, I will ask two more questions, and I think we should wrap up the webinar. So a question for Dr. Jadidoleslam. What would you expect of the satellite precision and moisture measuring during winter when upper soil might be slightly frozen? You are muted.
Very good question, actually. That's well, we cannot expect much from these satellites because the soil is covered and there is no emission going back to the atmosphere. And however, I know a few groups that are working on discriminatory analysis using the satellite observations from SMAP to discriminate the soil, the snow cover, and the bare soil. So answer is no, we cannot talk about soil moisture that much. And it becomes a little bit irrelevant for its application, because when the soils are covered with snow or ice, then whatever is precipitating or whatever rainfall falls on that ground it's gonna become runoff, or it's gonna, freeze. So that's one. Or and then when so the soil, or when we don't have agricultural activities during that times, so essentially we don't go into that, at least me, but snow people are working on that.
Thank you. So the last but not the least question is for Dr. Jin, and it's already in the chat. So Dr. Jin showed two maps of NACS and VOC for different time intervals before and after 2000. How much of that difference is due to the differences in satellite retrieval or quality of the data during two periods?
Okay, thanks for bringing these questions. And this is actually the questions that I'm trying to address from all the papers. So the essence of the paper is, so one of the technical difficulties of my paper is actually trying to harmonize observations from different periods. So as I just mentioned, that for the later 2013 to 2016 period, we're mostly relying on using the OMI observations. And for the early period, we mostly rely on using observations from like two older instruments like GOM and Xiaomeng. So these two satellite instruments have a lot of differences in terms of the resolution, data qualities, and also the overpass time difference. So what we are trying to do is that we developed algorithms to harmonize these observations for different satellite instruments. So the harmonization algorithm is kind of difficult to explain now, but I just want to say that the first is that these satellite products are retrieved consistently using the same algorithms, which is done through the QA4ECV project, which stands for the Quality Assurance Essential Climate Variables, and you can check it out from the website. So during this project, they have been developing the products that use the same retrieval algorithms and same prior profiles. So this is actually the fundamental step towards the harmonization. And the next two steps that we have applied is that we adjust the overpass time difference and also the resolution difference by comparing these two satellite instruments during the overlap period. And then we apply this difference of this overlapping period to the other period without OMI observations. So what we did is to harmonize GOM and Xiaomeng data with reference to OMI data, so that we can have harmonized data that can, and the difference in this NO2 and formaldehyde is largely due to these NOx VOCs rather than due to the difference in the satellite retrievals. But I also want to say that there are some limitations with our harmonization method, and there could be some differences that could be due to this difference in the qualities of satellite retrievals. But if we look at the long-term average, they seem to work fine.
Okay. Thank you very much. We are almost out of time, so I will use 1 minute to just talk about our upcoming webinars. And actually, unfortunately, we will not have a webinar for November because we are very close to the AGU, but we will have a panel at AGU fall meeting, which will be virtual, and I encourage all of you to look it up on AGU meetings. And I also put the webinar registration form, so you could sign up to get notified of future webinars, and you could use that to show your interest to present your works. And I have to mention that this webinar is free for public, but if you want to join the AGU GeoHealth community, you should first become an AGU member, and you can register on the AGU website. And finally, I would like to encourage you to please reach out to us, to our co-chairs, or please send me a message in the chat. If you want to join our committee, that will help you to develop your leadership skills and broaden your networks. With that, I would like to thank you all and our speakers for great presentations and conclude the webinar. Thank you very much.